Hi everyone, we are going to do some notes today on our inverses. We're going to keep trying to use those steps to find our inverse functions, and we'll also talk about a couple of cool characteristics that come up when we graph a function and its inverse that actually let us solve for an inverse in a slightly different way. So by the end of the period, you will be able to write the equation of an inverse function two different ways. So we'll start with the method that we learned yesterday. We'll look at some graphs, and then we will learn about another way that we can find inverse functions. So this question says, what are the inverse functions for each of the functions below? Use function notation and justify that each equation for the inverse works by showing the output for f inverse is the same as the input for f of x. So anytime we were trying to find an inverse yesterday, we were really focused on listing out steps, because an inverse is basically just reversing or trying to undo the steps in our original equation. So the first thing we're doing is thinking about what things are happening to x in our original function, right? The first thing that's happening to x according to PEMDAS is that x is being multiplied by 3. And then the second thing that's happening once we do that is we would subtract 6, right? An inverse function works by taking that output, whatever we would have gotten, sucking it back up into that function machine, and spitting out that original input. So in order to find our inverse function, we need to do our steps in reverse, and we need to do the opposite. So steps for our inverse function would be to add 6, because that's the opposite of subtracting, and then divide by 3, because that's the opposite of multiplying. So if we're trying to write out our inverse function, it's asking us to use function notation. Our function name here is f, so our inverse function is f inverse. And remember, we use that little -1. It looks like an exponent, but it's not an exponent. But we use that to say that our function is an inverse. So once we write our function notation, we'll write an x and think about the steps that are happening to our x. The first thing we wrote down was that we are adding 6, and then we are taking that whole thing and dividing it by 3. Okay. You can either leave your answer that way, or you could think of this 3 dividing each thing individually. So we would have x over 3, which is 1/3 x, and 6 over 3, which is 2. Those are equivalent. The blue one might look a little bit cleaner, especially if you're trying to graph. It's going to be a line if you're trying to graph that by hand, but either one are fine. So it's wanting us to also justify that our inverse is correct. So we're going to plug in some input into f of x. We'll get an output. And then when we plug that output into our inverse, we should expect to get the exact same input that we started with. So a really easy input that we can use here would be to use 0, which is basically saying that we are plugging in 0 everywhere we have an x. So that just ends up being -6. Right? We want to see if we plug in -6 into our inverse function, does that give us back out our original 0? Did it undo everything in our function, right? That's kind of what we're checking. So we'll check f inverse of -6, which means everywhere we see an x, we're going to put a -6, and I'm going to use that first form. -6 plus 6 is 0, and 0 divided by 3 is 0. So if you notice, we started with 0, and we ended with 0. Since our inverse function undid all of our steps, that means we have the correct inverse. Okay. All right, let's try another one. On letter B, we're doing the same sort of thing, thinking about what steps are happening to g of x, right? Looks like the first thing that we're doing to x is we are cubing, and the second thing we're doing is subtracting 5. So if we're looking for our inverse then, we need to do these steps in reverse, and we need to do the opposite. So step 1 for our inverse would be to add 5. And step 2, the opposite of cubing, is cube rooting, just like the opposite of squaring is square rooting. So writing down our inverse, our function name here is g, so we're going to name our inverse g inverse. We'll put our x, and we'll think about our steps. Step 1 says we are adding 5. Step 2 says we are cube rooting that whole thing. Okay. So here is our inverse, and we can check to make sure that our inverse is correct by making sure that if we put something into g and we get an output, and then we put that output into the inverse, that we end up where we started. So let's try 0 again, just because that's an easy thing to plug in, right? We have 0 cubed minus 5, so we end up with -5. If we take that -5 and plug it into our inverse function, our goal is to hopefully get back to 0, because that's what we started with. So let's see if that happens. We'll plug in that -5 into our inverse function. -5 plus 5 under our square root, or cube root, sorry, is 0. And the cube root of 0 is 0. So we ended back up where we started, which is great. So I want you to go ahead and pause this video right here and go ahead and try letters C and D. All right, so hopefully you tried those out and you spent some time trying to justify your answers. The answers that you should have gotten should look like this. So if you didn't get these answers, check in with a teammate, see if they can help you out. If your whole team is not sure, make sure that you're starring this problem or circling it so that you can ask for some help tomorrow. All right, so what we're gonna look at next is what the graphs of these functions look like, or the function and their inverse, and we'll actually figure out some interesting properties. So if we go over to Desmos, this is letter A, graphed, right? 3x minus 6 was our original function. X plus 6 over 3 is our inverse function. Desmos doesn't necessarily recognize the inverse notation that we use with that little -1. It doesn't know how to distinguish that -1 from notation versus an exponent. So that's why these are both plugged in as y equals. But basically what this question is asking us to do is to describe some relationships that we are seeing between the function and its inverse. One thing that I noticed right away is if I'm looking at a couple of key points, like my x-intercept and my y-intercept, they're very similar, except that our coordinates are switched, right? Our x-coordinate of 2 becomes the y-coordinate of 2 in our blue. And same with the zeros, right? They're switching places. If we check a couple more points, that's still happening. Our x-coordinate and y-coordinates are in opposite places. And we could check some other random points on our line. It looks like -3, 1 is a point on our blue graph. So let's see if we switch that coordinate. If we go to 1, -3, that's a point on our red graph. So every single time on these graphs, it looks like our x and y coordinates are switching places, right? We could check that same sort of thing with letter G or letter B. So we're looking at our x-intercept and our y-intercept, right? -5, 0, and 0, -5 are coordinates switched. Same thing over here with our y-intercepts and x-intercept. We could pick another point on our graph if we wanted, and it would be the same thing. So one relationship that functions and inverses have is that their coordinates, their x's and y's, are always switching places. And that kind of leads us to a little bit of symmetry that we can see on these graphs. If our x and y switch places, then we could say that y will always be equal to x for whatever our inverse is. For example, if our y in our red graph is -5, that will always be the x in our inverse function. Or if our x is 0, that will be our y in our inverse function. And so we see this reflection between our red graph and our blue graph, our inverse and our original, over this line y equals x, because our our function and our inverse are always switching, right? Same sort of thing here. If we go back to our lines from letter A, if I graph in y equals x, we're seeing that they're cut perfectly or kind of mirrored in half over y equals x, okay? So what I would like you to do right now is to pause the video again and go to Desmos and try to make a graph for letters C and D, right? Those were ones that you should have worked out on your own. And I want you to graph those and verify that our x and y coordinates are switching places and that they are reflecting over the line y equals x. Okay, and you'll write a little reflection about that here, right? Just confirming what we talked about in this video. So take a second, pause, go to Desmos, and we'll come back in just 1 second and finish the rest of our lesson. All right, so we should have noticed that our x and y switch places, our x and y coordinates are switching places on the graphs of our previous page. So we can use that idea as an alternate way, a more algebraic approach to always solve for an inverse function. So what that's gonna look like is we wanna first think of this f of x as a y just because we've been talking about y's and x's. So I'm gonna rewrite that f of x as a y. And since our x and y coordinates always switch places, what we're gonna do to try to find our inverse is to swap where our x and our y are in our equation. So if we switch the position of the x and y's, we end up with something like this. And our goal is gonna be to solve for y, right? That y is representing our inverse function. If we're wanting to get y by itself, we would need to add 6 to both sides and divide by 3. And notice we're getting the exact same inverse equation that we got earlier, right? So as an inverse, we would write f inverse of x equals x plus 6 over 3. And we could simplify that down a little bit more by dividing x by 3 and dividing 6 by 3 and make it look a little bit more like our slope-intercept form, or we can leave it alone like that. All right, so on letter B, same sort of thing. We'll switch that function notation to make it look like x's and y's. And since we know that our x and y coordinates always switch places on our graph, we can switch our x and y in our equation. And again, our goal here is to get that y by itself now. So if we're trying to do that, we would need to add 5. So we have x plus 5 equals y cubed. And the opposite of cubing would be to cube root. And we get the exact same thing that we got on the last page. So cube root of x plus 5. So I'd like you to take a moment and try to practice letters C and D with your teams. And you'll know that you did these correctly if you get the exact same inverses that we got on, I think it was page 5. Yeah, page 5. So for letter C, you should have the cube root of x minus 3. And notice how that minus 3 should be on the outside of our cube root. And for letter D, you should have 3x plus 4, right? So you can choose whichever method you want in general to solve these inverses. Now I've given you a couple ways. You can either focus on writing steps, or you can do some algebraic work by switching x and y. But for letter C and D today, I do want you to try that switching x and y method here. Just to practice that option. All right, so once you finish those, you are done with your notes, and you will just be responsible for completing homework 2 in your homework packet. And don't forget, if there were questions that you had today or things that you were confused on, make sure you write down a little note to yourself to remember to ask on Wednesday when we're back. All right, I will see you guys tomorrow.